So we're starting off the day right. Hopefully you guys got your wiggles out.
No.
Not really. Thanks for not having your cell phones out. Those waves are going to come in even after this class, so put that away for now. Earbuds. Thank you. Yes, I am. I just did it. Okay. Shh. Shh. We're starting to work with vectors today. If you guys have taken, where is it? Is it in bio? Where you guys do vectors as well? Hey? Vectors. Science. Where does it show up? Is it in vectors? Is it in physics? I thought it was, yeah. Oh yeah, definitely physics. I had to think about it. So you'll be using this again once you get to physics. We're going to do a lot of vocab, so just definition type stuff. We'll do a little bit of operators. Thank you. Not talking over you. So, a content objective today. I will find, write, and operate on vectors. Here's some of the success criteria. You can use magnitude and direction to show vectors are equal. Visual scalar multiplication, vector addition, vector subtraction. Represent them in the rectangular coordinate system, even though we don't call it X and Y anymore. Technically do, but technically don't. We call them I and J. So perform operations in terms of I and J. Find a unit vector. Unit vector should just make sense, right? It's a vector with magnitude 1. If it's a unit vector, then it only has one unit. Write vectors, and we won't probably get to the end here. Well, definitely we'll start off as far as we can. I'm not trying to hurry through this, but kind of trying to not waste our time either.
Wait, so x equals I and y equals j?
No. Hold on.
Wait,
Yes.
that just makes sense because
Yes.
it's
Yes.
alphabetical?
Yes.
I was like, what?
Yes.
Yes.
Kind of thinking about it.
So when we write the coordinates for this, is it going to be like...
Yes, I is X, J is Y. Okay. Okay. Let's get started. Vocab. Well, we have some of them. You definitely need to know vector. You need to know magnitude. And I should have had direction in there. Direction. And hopefully everybody knows what direction is, right?
No, what direction?
Direction. If you don't know direction, then let's just purchase you a dictionary here. All right, here we go. So vectors, quantities that involve both a magnitude and a direction are called vector quantities, or just vectors. Quantities that involve the magnitude but no direction are just called scalar quantities, aka scalars.
Okay.
Or scalars. No, not scalars, I'm just kidding.
Wait, what?
A vector has both magnitude and direction. Scalars have only magnitude, but they don't give you direction. I remember saying scalars when I was in school. I was like, scalars? Scholars?
Wait, how do you say it?
Scalars.
Scalar.
Scalars? Like scales?
I've met someone who actually
So
taught
Munoz,
What?
when I move on to college, I'm gonna come back as a major.
Cool. Yeah, people do.
No, you'll see me every day.
Oh, that's fine with
She's
me.
like, no, actually, like, I'm gonna see your class. So like, I'm gonna be in your class again.
I had a student that would send me problems through the Facebook, the chat, and I'd do them in there and I'd just send it back to her. She's like, thanks, that makes a lot of sense.
I'm gonna send you
Yes, I used to do
my
that.
entire test.
I don't get on it really, like it's there, and I don't even want to turn it off. If people can send me
On my sister's birthday so I can post her ugly selfies. That's the day I'm ready. She did it.
Oh, nice.
I only use Facebook to make my mom.
Are we good? Okay.
Oh, that's why you usually just tweet about it.
Vocab, vocab, vocab.
You sound so good.
What's the worst thing you can do?
We're good? I'll see anybody else, Ray? Ray, you good? Okay. How about some common sense vocab?
Yeah.
A line segment to which a direction has been assigned is called a directed line segment.
Wow.
Where you started is called the initial point, and where you ended is called the terminal point. The magnitude of the directed line segment, and you can see kind of like ray notation. You guys remember rays from geometry? Very similar is the length, but we denote it by using the little double bars as well on the outside to tell you that it's a magnitude there. A vector is directed line segment.
They're gonna like add this to this
So we're just like making scenarios to solve.
Well, the way you're sitting is kind of weird.
Yeah, I know. It's not comfortable the other way.
This is gonna work.
Huh?
We've done all right.
I don't think I tried.
I'm just kidding.
I can see him just.
He was.
6
He was doing circles around. He looked like a dog.
We're not gonna go there. We're just not gonna go there.
All right. We're good. Ooh. We're good?
Hold on.
No, not good?
No. I'm just gonna take a
What, are you writing the whole thing?
She does.
Dude, the slides are on my math lab.
I just like taking pictures and writing in my notes. I don't like
The whole slides are on math
And
lab.
it's on.
And it's on YouTube, immortalized. Forever.
Wait, have you watched Us yet?
I've watched you since August.
What?
Yes.
Don't take that as a no.
Doesn't even know what it is.
It's a movie.
It's kind of crazy. It's like the background of the story. Think about it.
Okay. Oh, this is small. Let's do this a little bit bigger. Okay. A little bit better. If you're going to print it as a vector, it's a bold letter V and sometimes W. You can use W. Because we're going to be comparing two different ones, right? So we have a vector V and a vector W, or if you want to call it double V, or
Double V.
it's a double V.
How was spring break this
I mean, it looks like a double. Wait a minute.
It is a double V. What are you talking
I spent
about?
all break sick again. Went home Friday sick, fever, and pretty much in bed all Friday, rest of Friday, Saturday, Sunday, part of Monday. Woke up Tuesday, killer back pain, had to tuck through it. Chiropractor Wednesday, Thursday, Friday felt a little bit better. Saturday, Sunday had to go shopping.
That was your spring break?
That was my spring break. Sick.
Would you rather be sick over break than
Okay, thank you. So, vectors. Here's how we're going to write a vector. We're going to print it out using your LaTeX. But if you're doing it by hand, make sure that you do that with a little ray looking thing on top. That's for your vector. Let's talk about magnitude. Magnitude, you're going to add the double bars there. On the what?
This is magnitude?
This is magnitude. You want to use those double bars. Double bars, double bars.
Wait, this is on my math lab, right?
Yes.
He
It's the absolute value. I always think more like step function, but step function has a closed double bars kind of thing. It's kind of like a double bracket.
Yes, this is how you're supposed to write it. You just like rest your
Hey, Trevor.
fingers and
You should go back to doing baseball.
We're good? No, 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 no.
You should do baseball meetings.
No. Okay.
I haven't played in years, so.
What are you?
Second, short, outfield. Always. Okay, so
Left outfield.
also your left foot. I can do any outfield.
Are we good?
Yes.
Okay.
They don't think struggle.
Equal vectors. Equal vectors. If two vectors have the same magnitude, we call them equal vectors. So, see these two vectors have equal magnitude, equal. Though the direction is not the same, the magnitude is the same, therefore equal. These guys are going in opposite direction, magnitude is the same, equal. Over on the end, both in the same direction, but one's shorter than the other, correct? Therefore not the same magnitude, therefore
Not equal.
not equal.
For B, how do you know it's a magnitude?
Huh? Right now we're told that these are the same. Later on we'll calculate them. What's your question? They're telling us. They're telling us. Because the vectors have the same magnitude and the same direction. Vector V and W have the same magnitude but different directions. Still good. Vectors V and W have the same magnitude but opposite directions. Vectors V and W have the same direction but not. But different angles or different magnitudes.
So they're equal in their first.
No, they have to have both. I said that wrong, didn't I? Okay, correction. I just said that wrong. This is the only one they're equal because they have the same magnitude and the same direction. These are the same magnitude but different directions. Same magnitude, different directions. Same direction, different magnitudes. This one we call equal. Okay. Go ahead. It's actually pretty simple. You ever heard of this thing called Pythagoras theorem? It just shows up everywhere, doesn't it? Well, they don't call it Pythagoras theorem. They call it. That is fakeness. That is fake. Fake. Okay. You guys ready to try this? Okay, I've got two different vectors here. I thought it was going to be bigger than I see. Okay, so here we have, can you guys see the coordinates okay back there? Okay, cool. So we want to just show that these two are equal. How can we do that? Well, are they going the same direction?
Yes.
And do they have the same magnitude?
Yes.
How do you know they have the same magnitude?
They have the same slope.
Because they look the same? Let's figure the direction first, okay? I'm going to use this old thing called a slope. I've got to go up 1, 2, 3, 4, right? So the slope here is up 4, 1, 2, 3. So there's the slope on this guy. And then the other one they're calling U. I'm going up 1, 2, 3, 4. And then I'm going to the right 1, 2, 3. So are they going in the same direction?
Yes.
Definitely, because the slopes are equal. Slopes are the same. Now, do they have the same magnitude?
Yeah.
Yeah.
Well, yeah, because if I did Pythagoras theorem on one, I should expect to get the same on the other one, correct? 4 squared plus 3 squared is going to give me that distance squared. So these are definitely equal. That was easy. Let's move on. Scalar multiplication. Man, that's very small. Can you guys ever see my vector V? Here's my vector V. I know. No, vector. Oh, you want that? There's my vector V. I was going to try to make it bold. If. Thank you. let's say that this was vector v for some reason. Salud.
Bless you.
Okay. And I put a scalar right up front. That's telling me that I want 2 times my vector, correct? What's that going to do to my graph?
Stretch it.
How much?
2 times.
Twice as long, right? So it should get twice as long. Let's pretend that that's correct.
Oh, okay.
What if I made that 1/2? Then it should go about half the distance. Close enough? Okay. What if? What if I did?
It goes the other
It goes in the opposite.
Ah! It's going to go the other direction, right? It's going to change by those quantities. What are we simply doing with the vector coordinates? Just multiplying them by that, right? Okay. Do I need to wait for anybody?
So like if it were that one in your coordinates were like 1, 1, and
They
then
become negative 3/4, comma negative 3/4. Simple enough. But you need the definitions. You can't play the game if you don't know the rules.
I'm still writing that.
Oh.
too. I'm still writing definitions.
Oh, my bad.
I need to do one.
That's the wrong slide. Oh no! Okay. You guys okay with this slide?
yeah.
Here's a definition of it in math talk. If k is a real number and v is a vector, and vector kv is called a scalar multiple of vector v, the magnitude and direction of kv are given as follows. The vector kv has a magnitude of absolute value of k times the magnitude of v. We describe this with absolute value of k times the magnitude of vector v. The vector kv has direction, that is, if k is bigger than 0, then it gets multiplied. Otherwise, you go the opposite direction if it's less than 0, which makes sense because now it's a negative vector.
Is that just saying the number in front of it, if it's negative, you go the other way?
It's saying exactly what we said in the last slide. But this is the mathematical jargon.
It's the mathematical terminology.
Tis mathematical, tis the content-specific language. That's our language objective, right? We good?
Yes.
Time to add them up. Let's plus them.
that
That's
was
content-specific language.
Oh, that's gonna be nice for the video.
You're welcome, video. I can change the slide?
Third hour?
Third hour, it's sneeze?
No, like the way you sneeze, it just sounds like everything is coming out. I was like,
Pobrecito.
Or like
Okay, let's add them up. The sum of vector u and vector v denoted by u plus v, universal sign for addition. We're going to call that the resultant vector. The resultant vector, look at it right here. Okay? And here's how we find them. We're going to position them in such a way. We're going to start with u, right? So here is vector u. And I want to make sure that I take the other vector and I kind of put its starting point at the ending point of the other. And then what we get from starting of the first to ending of the other is the resultant vector. Yeah? Ever see that?
Show you.
So if I had, I don't know, this vector and that vector, then I would have to move.
Oh, it depends on the direction they're going.
Oh, estate. Yeah, it really does. So I would have to take one vector and I would put it at the end of the other,
Oh, okay.
and then my resultant vector would start here and it would end there. And this would be my result. Make sense? Should make sense though.
Oh, because you're taking, so it's like
Think about pool.
taking the average.
Think about the pool. If I hit the ball this way and then I have another one that hits it this way, its trajectory will kind of end up looking like that in the long run.
I got you. I I was just.
I like pool. It's a really fun game.
I like carambola. Billiards.
Yeah.
Not pool. Billiards. Have you ever played billiards? There's no pockets.
Yeah.
And there's what? Is it 3 or 4 balls?
I think it's.
With billiards. You got two. Are you serious? That's like the OG game. You have to, yeah. And there's a lot of masters with billiards, actually. No, billiards. I'm pretty sure that's what it's called.
I look it up.
Yeah.
I always thought they were the same. How you spell it? B-I-L-L.
Like Bill,
Is it
and then IARDS, billiards.
And you know how it's.
It does, huh?
I feel like it is a type of.
It's a place.
Okay, you guys good? I can wait.
What's the difference?
There should be pockets.
There's 6 of them. Like all the pictures, 12-year-olds.
Especially as I can't really do it. I'm wrong. So I play short ones. I used to play short ones. But I played this one. I don't know if it was different. So I had to step in more over it. And I stepped behind it because I knew it was.
No, there's no pockets.
We're supposed to do with the ball.
You're supposed to. You have to hit one. You get one hit to the white ball, but you have to hit one. Then you have to hit the side before you hit the other one.
Also, it's big shot.
Pretty much. But that's over and over and over and over and over.
So every time you hit one, they just kind of like right there.
And you have to play them on the land. And then once you don't hit both of them, then it's the next person's turn.
Do you ever take the ball? Wait, just like
No,
that.
they have to stay there. They don't.
You just like hit him and you just keep hitting him.
I'll show you. Yeah, you just wherever they fall, it's how you have to play them.
So it's basically, I've been seeing this one.
Yeah, it's all angles.
And I had to.
It's straight up geometry.
It wasn't open-handed.
Huh?
But I figured like it's like wrong way to go.
I mean, I think everybody knows like that though. Okay,
Kind of like it looked good.
is this one okay with you guys? Show me a thumbs up. Can you visualize this addition?
Does it matter which one you put? Like, does it matter if the shorter one was at the other side?
Well, it depends what you're doing. U plus V or V plus U. So we have to denote one of them to have a name.
Does it change the length? Like if that goes at the end, can you see if the
Well, technically no, because see how I put this one there?
yeah, see if the blue?
And then if I move the blue line,
Oh, it's just for
it'll be the same.
coordinates.
But that should make sense because addition is, what's the magic word? Addition is commutative. I can have them in any way, I still get the same result.
Alright, so like basically,
I can't hear you.
kind of like a really simple version of spiral zeros because they seem more simple.
You know what? I always think Pythagoreans as well.
Yeah, because like if you think about it, oh, this side plus this side equals this, you don't forget square. We don't need square it.
Yeah, kind of.
Yeah.
I see what you're saying there. That makes a little sense. All right. Subtraction. 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 It's not as straightforward. Let me go and show you that one real quick. Yeah. You guys see that? Okay. So this is the difference between V take away U. V take away U. I want to highlight V. V is right here. Okay? So there's V. I'll use green for U. Here is U. Right? But we're not adding them. We're subtracting them. Okay? So here's what we're going to have to do. Once on the terminal side, we're going to go the opposite direction. Once on the, sorry, not terminal side, the beginning side. And once on the terminal side, we're going to go the same other direction. So that's what we're going to get there, that distance between those two. And that's this one here. I ran out of colors. That one would be your V minus U.
Can I ask you a question?
Okay? What's up?
Try.
You're going to end up getting some kind of a parallelogram?
Is this the same as this?
No.
How do you erase
You're good. Thank you. Okay. So you're just looking at that diagonal inside that parallelogram.
Yeah. When you sit down, the seat doesn't stay.
Can I what? Do you see the parallelogram in here?
Yeah.
So that diagonal inside is going to be v minus u. Because you're subtracting. So u, this is u, correct? But you're going to go the other direction. So what we're going to do is we're going to... I saw that going down in slow motion. No! So to get this distance, I mean, it's there for us, right? But we're not going to be able to see it. So we're going to go the opposite direction first. I want to take that same distance. I want to plop it up here so I can create this little parallelogram. Because then the difference would be that right there. The distance from vertex to the other vertex. Okay? But this is always going to be that point that we're initiating on. Okay?
Let's say v equals to v minus u.
V minus u is equal to v plus the opposite of u.
Wait,
Wait, why do you want to know what that's from? What would you want, like, where he and you are at?
Say that one more time.
Why do you want where
Why do we want this? That's v minus u. That's when you apply an opposite force to something. It's going to shoot off in the other direction. It's not going to keep going forward, right?
Also, you need to find the resultant vector and then it's negative, basically.
Yeah.
Is that v minus u like
That is v minus u,
the
correct.
same as like if you had the v and the u and you connected them? Is that the same way?
No,
I'm just like
it's different because now you're applying an opposite force.
I know, but like, it's not the same. Like, I know it's not the same placing, but is it the same like if it's 5, is it 5 between v and u? Maybe.
Is it 5 between v and u?
Like, say if v minus u is 5, yeah, is that like 5 too?
No. Oh, I see what you're saying.
Cause like all the lines match up. So I'm just trying to like. Cause like you said it's
I see what you're saying.
Yeah,
I see what you're saying.
It's a parallelogram and then u, like the green u is in line with the other.
No, I see what you're saying. I did. You know what? I want to say yeah.
Cause I feel like you're gonna give us a weekly problem.
No, I want to say it's going to be the same because I can see this parallelogram.
Yeah.
So that's also that.
Yeah, it has to be.
Yeah. That's right.
Has to be. Now, the magnitude would be the same, but not necessarily the vector,
Yeah.
because you'd be going in a different direction. So yes, the magnitude would be the same. I can see that mathematically there.
Yeah, basically.
Okay. So, you can call it that. You can call it that. Okay, we go?
Yeah.
All right, I's and J's. I's are on the X, J's go up and down. So when we talk about I, we're talking about the value on X. When we talk about J, we're talking about the value on Y.
I shouldn't use I, because like when I see the I, it makes me think of the
Square root of -1.
Yeah.
I think we've used all the alphabet, so now we're just recycling
26.
it.
Well, where's P? Oh, we're gonna probably get
Where's what?
P.
That's the initial point for that's the symbol for the initial point.
But D.
It's right after C.
I already have it.
Right before E.
They use it for the distance formula. Okay, it's for coefficient sources.
I'm not sure if I'm liking that back there. You guys getting cleaned out over there. Get better, please. Okay, rectangular coordinates.
Hold on.
This should show different color. Do I really want to do that? That's kind of a lot. Jackie, give me a coordinate. I need quadrant 1, please.
1, 1.
Something more fancy?
4, 5.
Sounds good to me. 4, 5. So we've got some coordinate out here. We're calling it 4, 5, and I want to give that to you. Give you this vector in rectangulars. Then we're just going to say the vector is. We'll go vector. 4i plus 5j. I don't know if you want that. You guys handle that?
That's what I just said.
You know,
It's imaginary.
it's not an italicized I. This is the square root of -1. This is just I. That was ridiculous. That's not true. I'm just lying. I forgot my little arrow. Okay. Does that make sense? Pretty simple? Okay. So here's the fancy talk for that. From vector. Vector v from 0, 0 to ab is represented as vector ai plus
J.
The real numbers a and b are called scalar components of v because they're stretching them in that direction. Be quiet.
That's how you find the
That's math. Don't laugh at math. A is a horizontal component, b is a vertical component.
Wait, okay, so the same way that you get rectangular coordinates is the same way that you find the magnitude?
No, this is
Oh, the magnitude of.
say that one more time for me.
I
Guys, I can't hear the questions.
I read it wrong. Because I was reading the magnitude is v equals, but it says the magnitude of.
You still have to go with the Pythagorean theorem and figure out what that distance is. That would be the magnitude there. Yeah, see?
Oh, yeah,
It's a squared plus b squared. And take the square root of it. Remember, double bars represent the magnitude of the vector.
So that's how you go from rectangular coordinates to find the magnitude.
No, this is giving me the vector in rectangulars right here. Okay? And all it's saying is that this is the scalar on I, this is the scalar on j. Together we call that a linear combination. This is still how we find magnitude. We're still going to figure out what the distances are, right? So let's go back to, what did I have? What did you say, 3/4? Can we go back to this one real quick?
She said 4, 5.
Ah, never mind. I thought it was 3/4, because then we were just like, oh, magnitude is 5. Okay. How are we doing?
On time we have 5 minutes.
No way.
Really?
Yeah.
See, wait.
This class went by real quick.
Well, you got almost 30 minutes
Because
of
of the chairs.
Yeah, I think it's
wiggling.
because. Oh, yeah. Yeah, I felt like.
Okay, let's take a look at this right here. They want us to sketch the vector 3i minus 3j and then find its magnitude. Well, 3i minus 3j, 1, 2, 3, 1, 2, 3. Here is, there it is, right? Everyone okay with that? Find its magnitude, we're going to do 3 squared plus 3 squared and then take the square root of that. So we've got 9 plus 9, 6 plus 6. It used to be 6. What's that become? 3 radical 4?
Yeah.
3 radical 2? Thank you. So there's our magnitude. Magnitude of...
Wow, I love how shaky the screen is.
It's because they're walking upstairs. Yeah, you don't see it from back there so much, huh?
I don't see it.
Right here, I'm just going...
Yeah, that's what we're like.
How we doing there? I'll change that.
I cannot write it.
You know what? We'll stop here. Hold on. I'm just gonna stop this.
Oh my god.